So hello everybody, and welcome to this webinar on tapping into geothermal energy and renewable heating. Uh, my name is Jared Leake and I'm the CEO for the Australian Alliance for Energy Productivity. A2EP is much easier to remember. I'd like to begin this webinar with an acknowledgement of the traditional custodians of country throughout Australia and their connections to land, sea and community, and pay my respects to their elders past, present and into the future. For those of you new to A2EP, we are an industry association funded by these fabulous range of members that share our vision of improving energy productivity and decarbonisation. This fantastic set of members absolutely cover all the different areas of technologies and consulting and research. It gives us a beautiful broad base of knowledge to draw upon, and many thanks to those members. Just a little bit of housekeeping. Today's webinar will be recorded and issued out to those that are registered over the next couple of days. We certainly have got plenty of time assigned at the end of the webinar for questions today. So please type your questions in that Q&A box and then upvote others. And we may be able to get our experts to answer those questions during the webinar as well. So plenty of opportunity to consult here to the experts. And so yeah, that's it for that. We've got the recording, as I said, coming out in the next week. This is part of a month of heat pump. We're celebrating heat pumps this month. This is our fourth webinar. If you go back to A2EP's website, you'll see a whole range of other webinars this month on heat pumps, looking at high temperature heat pumps, looking at projects, looking at opportunities to optimize them. And we come fresh off some great site tours just yesterday, looking at heat pumps and how they're implemented in aquatic centres. But today we're focused on geothermal. We think it's a very important part of the mix, and it cannot be forgotten. So from the A2EP team, don't have anyone joining me. We've got an honorary member, Kristian Gjoka from University of Melbourne. Kristian, thanks for joining me here today. You and the team at University of Melbourne are probably must be the leaders in the country when it comes to geothermal and ground source heat pumps. You've got Graham Beardsmore there. You've got Rachel Webster and Bazad Rizmachi as well. Fabulous team. But Kristian, thanks for joining me here today.
Thank you for having me, Jared. That's very flattering.
Hearing from the experts, this is great. And just before I hand over to Kristian to help us with a bit of context setting here, just wanted to share with you all a great report that's come out yesterday, come out from the IEA, the future of heat pumps in China, and a lot of the information in there and recommendations completely applicable to Australia, and some really good insights there. One of the tables here that I'm just sharing with you is this urban heat island effect. And this is across Chinese cities, of course, but I think if you look at the ones on the right-hand side there, the climate is going to be quite similar to ourselves. And you see that extra 1 to 2 degrees impact that this urban heat island effect is having. And geothermal ground source heat pumps offer a solution here, and that's why I think it's so very important. Another one I just wanted to bring to everyone's attention why we think this is important is the need for efficiency in winter. We're going to this renewables here in Australia, and you'd say South Australia is probably the most representative market of where the rest of the electricity market is going. And this just recently taken from the South Australian market, and you can see in that period in that winter period where solar is coming way down, the solar production there. And so this is what most of our renewable supply is likely to look like for all of Australia. So what do we do in winter? And this is where we think energy efficiency through those cooler months is going to be so very important. And again, another reason why we like to look at ground source heat pumps, because of the advantage they have there in those colder months. So there's a couple of reasons. Kristian, over to you. A couple more reasons for us to look at
Thank you, Jared.
thermal.
Thank you. So I might just go back to looking at the bigger picture. If you we move to the next slide, please. So the bigger picture when it relates to energy demand and the heating and cooling sector. So as we stand today, we're looking at a significant part of our overall energy demand dedicated to heating and cooling. Just about 50% of all the energy in the European Union goes towards heating and cooling as per the European Commission. And this is in a context of net zero pledges by many countries around the world. And moreover, in a context where about 3/4 of the population are expected to be living in an urban area in the future. And to reach net zero, it seems that all roads lead to electrification for the heating and cooling sector. Next slide, please. However, that does not come without its own challenges. So we need to be aware, we need to be conscious about that. Thank you, Jared. So electrification, what does electrification mean for the heating and cooling sector? That means heat pumps. And we've seen a steady rise in their use in the heating market, especially. And we can see here, for some countries, we have a double-digit increase. For some countries, we have a manifold increase, like the Netherlands, that starts from near non-existent heat pumps to 20% of the whole heating sector in just about 7 years. So the share of heat pumps seems on the rise. From 2020 to today, we've seen a 30% global increase in the sale of heat pumps. Next slide, Jared, please. China seems to remain the top 3, both in the manufacturing and as a market for heat pumps. We can see here the latest IEA projections that Jared mentioned in the latest report, both in the stated policy scenario and in the announced pledges of China. We see a steady rise in heat pumps, and we see here in green that the ground source heat pumps will remain a significant factor of the overall ground source heat pump mix. Next slide, please.
Oh, sorry, that's what we had there.
Thank
Kristian.
you.
Yeah.
So just to set the tone, heat pumps seem to be on the rise, and ground source heat pump will definitely play a role, just in terms of their overall better efficiency. They save us space, and as Jared mentioned, they can help mitigate or avoid exacerbating the heat island effects that would come from using exclusively air source heat pumps.
Well,
now, keen to hear from the experts.
Absolutely. Thanks, Kristian. And yeah, thanks for those highlights from that report. And yeah, out now, I think if you just Google that future of heat pumps in China, you'll get that report and plenty of good info in there.
Yep.
Really cool. Right. Okay, so here we got a great lineup of speakers for you today. We are going to start with a bit more focus on geothermal, and then move into the how you'd maybe integrate that with heat pumps. And we thought we'd kick off with the best and biggest what's happening with geothermal on the East Coast. And that's what the work that the Latrobe Valley Authority is doing. And so we've asked the Senior Manager for Regional Programs and Energy, Ashley Hall, to join us. And Ashley's worked with this for many years, and has seen some fantastic project happen there in the Latrobe Valley. And just recently been following this up with Ashley, and is absolutely blown away by the potential there. And I thought this really needs to be more better known, and see this as a fabulous opportunity. So Ashley, what I'll get you to share your screen and take us through what's happening there down in the Latrobe Valley.
All right. Can everybody see that?
Hasn't come through at the moment. And of course, I'm ready with the backup slides if need be.
That one there. That's because I didn't push the share button.
There it is. We're in business. Over to you, Ashley.
There we go. So, g'day everyone. I'm Ash Hall, Energy Manager at the LVA. So the Latrobe Valley Authority is a government authority that was established in November 2016 after the announcement of the closure of Hazelwood Power Station.
Ash, we've got this, the words come up there on the screen. We can see
Whoops.
the script there.
Yes. No. So we had two major directives. One is about the immediate response for the workers, but also the supply chain. And the second response is really where this talk is going to, is about the long-term strategic transition of the region. So working with the region's strengths, energy was, identified early as a major powerhouse of the region, and within that, geothermal was identified as to become a focus area because of the evidence. So, it's been well known since the 1950s that there's plenty of warm water sitting under the aquifers in Latrobe Valley. Innovation Network was formed, which involves academia, government, industry, and community to research, the evidence or create the evidence around uncovering our competitive advantage. So we're very blessed to have Dr. Graham Beersmore and Professor Rachel Webster in the Innovation Network, and they're really helping us driving that work forward. This is the Traralgon Aquatic Centre, which is the first, or it's the only operating aquatic centre in the state using a geothermal heat loop. It's basically a closed loop, so we bring water from the aquifer, passes through a heat exchanger, and then is put down to the same aquifer. So there's no water loss from the aquifer. It's really just the heat we're using towards the swimming pool. If I keep this pretty short, it costs $3.9 million to install the geothermal system. It is saving the Latrobe City $700,000 per annum on gas bills. With a project of less than 4 years, return on investment. And what that has done for us is shown the evidence around the great resource that sits within the Gippsland Basin, but is also applicable over near the Colac Otway Basin as well. And what we know is that that heat source really matches well with the industry sector as well, that are using low heat resources. So what we know, is that that low grade heat, which is up to sort of 70 or 80 degrees, when coupled with heat pumps, we should be able to get 2 degrees of about 120, and that covers a lot of the industry that is certainly situated across the region. Just move to the next slide. So then thinking about these sectors here, we can see that, the understanding of the coal-fired power stations that are closing down, there's a lot of available land. And if we think about, well, what can that look like for the future of Gippsland? The culture of Gippsland is energy, and it's also food and fibre, and coupled with those two, they're coming closer and closer together, thinking about, industrial scale hothouses that are growing food for the nation, using that geothermal heat as that basis of resourcing, thinking about, food processors and industries with low-grade heat sources, space heating. So we're looking at hospitals, aged care centres, schools, university campuses. The photo there is one of the broiler farms. Lots and lots of interest and conversations around heating, using low-grade heat to heat broiler farms, because at the moment, they're a fairly high gas usage. We think that we can create a low carbon chicken. You've heard that for the first time here today. We'd like industry to embrace geothermal energy and really showcase that that this is a really excellent pathway to decarbonising their industry without having to retrofit a lot of machinery and, high capex to move across to a low carbon future. In most recent times, we've had interest from ion flow batteries and thinking about the storage of energy. And because we can use the temperature, the 70 or 80 degree water to flow through the battery technology, keeping that warm has a much more efficient rate and a better return on investment. So could Latrobe Valley be the small battery of the nation? Possibly. That's what we're here to explore. Jumping to nearly my last slide is, so the Latrobe City's leading a piece of work, and this to the normal eye would probably look like just another industrial development. We're working with Regional Development Victoria to establish a design for an industrial heat loop. So how can we use geothermal as an attractor to businesses that have a heat demand, but also want to, move towards showcasing a low carbon future. And so the red lines on there are not just within the industrial setting, but also you can see the shopping centre north, and there's a education precinct as well. So an industrial heat loop is something that is fairly well known in Europe and across the world. This is probably a first for Australia, and we'd like to showcase it here in Latrobe Valley and use our resources as an attractor to economic development. And my last slide is this is about the activation of geothermal. It has happened through the innovation network, and it's happened through using evidence. Certainly become an integral part of, the region's transition and touches all four of our regional strengths. So there's energy, food and fibre, health and wellbeing, and tourism. Thanks very much, Jared.
Ash, many thanks. And I recall some amounts you're saying in earlier conversations about the quantity of energy available. It was almost too big to grasp, but thousands of petajoules or something to that extent. It's just enormous what you guys are sitting on down there.
Yeah, absolutely. There's something like 6,000 square kilometres, the size of the aquifer. So it actually runs from Latrobe Valley. It actually goes out under the ocean below the oil wells, believe it or not. So, it's a very large aquifer. The opportunity is enormous, and we're working towards not just showcasing that, but making sure we've got regulations in place to manage that as sustainably as we can.
Yeah, brilliant. And 70 to 80 degree hot water out of the ground, and I think you mentioned that Colac type area. I know they've got that in Perth as well. Not everyone's got that, but there's waste heat nearly everywhere coming from data centers and what have you. So and making that usable. And this is where we're going to turn to our next presenter here. 70 to 80 degree heat, okay, that's usable for a lot of commercial buildings and some agriculture and things. But once you start looking at sterilization and requirements for food and beverage production and for cooking, that's not going to be enough. So we thought let's now say, how can we use this to get even more out of it, so even more than just the commercial side of things. And to talk about that, I'm going to invite Simon St. Hill from gTET to give a presentation on how that can be upgraded and utilised. Simon's been working with gTET for many years, working on this since 1996, and started off doing organic Rankine cycle projects and lots of different heating and cooling projects. And gTET is one of our most innovative companies in this country, and so it's fantastic to have Simon join us and give us a presentation on that one. Simon, I'll get you to share your screen and tell us about what can we do with this this heat and get more out of it. Over to you, Simon.
Yeah, hi. Thanks very much for that introduction, Jared. Yes, yeah, I'm the technical director here at gTET, and yeah, so we're going to talk about using geothermal heat for industrial purposes. Exactly the project that Ashley was pulled up there on his second last slide, the smart geothermal industrial loop there down at Traralgon, and some of the work that we supported Melbourne University in undertaking. Yeah, with Kristian actually. So, yeah. Okay, so before I get into those details, just a bit of a talk about the general principles. Using a geothermal resource and say variable renewable energies, we can take that resource and pump the heat up to 120 degrees, no problem, as you mentioned. And actually now, as Jared was talking about earlier, with a better higher temperature heat pumps that are available, we can go to 150 degrees saturated steam. Yeah, so once we've got it up at that temperature for industrial use, we'll generally store the heat because the industrial use is a bit variable. Okay, yeah, so I'm assuming everybody who's watching this knows how a heat pump works, but just specifically in this case, we're taking the water and putting it into the evaporator. That makes it much better than an air source heat pump because the approach of the heat exchange is much closer, so it's much better, and you can lift it up much higher. One of the other things is generally industrial processes use a small delta T on the hot side, maybe only 5 degrees. For that reason, we generally prefer to use low GWP HFO refrigerants. They work well there. The CO2s of this world are really, really good at lifting, say, an ambient water supply up and making it quite warm. But if you're dealing in a 120 or 100 degree space, then those refrigerants seem to work better. Yeah, so that's, you may see that image in the top right look fairly familiar given a previous presentation. Yeah, so this particular project that we're supporting on, they determined that they'd have a 60 degree geothermal resource at this location from about a 600 metre depth. There's a whole bunch of modelling done on different options, different consumers and so forth by Princess. And yeah, we supported in terms of what the takeoff flow should be, heat exchanger selection, heat pump sizing, efficiency, cost. We come up with a generalised piece of equipment to go into each site so that the interface to the loop was the same with similar control system and so forth. And plus, of course, also just general industry-based thermodynamic support, like what was practical in the industry environment. Okay, so the results, just one slide on the results from this project. There was two basic concepts. One was the direct single pipe and the other one was the indirect double pipe. The indirect double pipe is like your traditional ring main type system. And the direct single pipe, because you have to re-inject it, there's some, you want to transport the water to another location if possible, rather than doing angled drilling and all that sort of stuff. Not my area of expertise, but anyway, so I was a bit skeptical, to be honest, about the direct single pipe because, of course, consumers are not re-injecting, but returning the cooler water back to the main heat pipe. So the downstream consumers have to add more heat to boost their system. But as you can see on the top right, yes, the parallel indirect loop traditional ring main system is slightly more efficient. So the y-axis there is a bit difficult to read, but that's basically the amount of energy you've got to put in to deliver the heating needs. So we're assuming the heating needs are constant and how much do we have to spend to get there. And but you can see, yes, it is better, but maybe not worth the capital cost of running, duplicate plumbing all everywhere and all the additional resources. And especially you look at the bottom chart, when you compare it with the traditional equivalent, which is a gas system, whereby there was a total saving of about 20 gigawatt hours of energy required to deliver the heat to the consumers. So in this model, there was three sites using the heat pump and 2 sites using just direct geothermal resource. Yep. So one of the things mentioned was industrial users typically have quite a lumpy usage of heat. Most lumpy would be, say, food processing, where they use maybe 80% of their heat in a couple of hours doing their clean in place type applications. And so they'll need some degree of storage. So clean in place would typically just use a stratified water tank to do that. For other industrial processes, it may be more appropriate to use a PCM material, especially where the storage space is an issue. So PCMs can deliver a megawatt thermal out of a 7 metre cubed volume, which is quite efficient. So that those solutions also go well into the industrial space there. Yeah, just a general talk about COP, and Jared was talking about this earlier. The source temperature has a massive impact on the COP of your heat pumps. Now, this is just a general plot. It's not specific to this project, but as you can see, you know, if your source temperature is up high, you're already in a good range. And with those heating loads in winter, air source heat pumps, you may be down at that 10-degree line, really struggling. So that increases your plant size to deliver the heating that you require and increases your energy consumption. So using the geothermal resource improves your payback by reducing your capital cost up above ground and reducing your energy consumption. Yeah, so that's basically a quick 5-minute overview of the heat pump of the gTET involvement in this project and heat pumps in general. Thanks very much.
Thanks for that, Simon. So I'm seeing there, hearing you saying that the COP is going to be greatly boosted by using this sort of lower temperature resource there. Kristian, I'm not sure Kristian's got some further or anything further to add there since he's involved in that project. But I also see there's a bottling, you had a bottling line there and a dairy. So there's a whole lot of industries that could potentially be using this. Kristian, anything further to add on that one that you guys, because you've been working on that project too?
I think pretty much Simon covered the most important parts. I would just add maybe on the series, the single loop, that probably, I agree with Simon, wouldn't be the first approach, but in this particular case, it just happened to work out that some of the users had very high temperature requirements, and we placed them upstream, and then all the other users that had lower temperature requirements, such as the greenhouse and the aquatic center, we knew that they could handle a lower temperature because they were using direct heat. So that it turned out to work out in this case, but that has its own challenges, because then you're limited to where the end users can be, and they need to be in a certain sequence. So just to add a little bit more color to that.
Yeah, and certainly this idea of a precinct approach is getting a lot of traction around the country, where you can optimize the capex and what have you. So yeah, interesting to see how that was modeled out. Very good, thank you. Good. So that's sort of a geothermal resource, how to get the best out of that. I thought we'd take a turn now and start looking at ground source heat pumps and geothermal in a wider sense, and different applications where it is being used already. And to kick us off there, we've got Yale. Carden is the founder and managing director of GeoExchange, and is also an honorary fellow at the Sustainable Business Research Centre at University of Wollongong. And after 30 years experience in the sustainability space, certainly plenty to share. So Yale, over to you, and looking forward to hearing about how geothermal is going to help with this larger energy transition.
Well, thanks, Jared. I'm just confirming that's visible now on the screen.
We've got it. Got it. Thank you.
Awesome. Cool. Thanks. Look, welcome everyone. Thanks for the opportunity to have a chat here. I'm going to talk about, I'm going to keep it relatively high level and let some of the others dive in a little bit deeper in terms of the detail of heat pumps and that sort of stuff. I'm going to mostly looking at the role of geothermal or geoheat, as a lot of people tend to call it. I think mostly to avoid some of the confusion with the electricity side of things in the broader energy transition. So I think we all know we're in a transition. We're not doing some sort of trendy thing at the moment. But what we've seen with the transition basically is we've gone from appliances back in the day of your dishwasher, your aircon, whatever, had a star rating. We then looked at buildings with Green Star. We've had a lot of these overlap as well, of course, in a time frame. Renewable energy, so there's a geothermal component there. There's a geo component in the heat pump side on the appliance scale. But mostly what we're talking about here is the energy demand side, a concept that we're sort of talking a lot more about a thermal demand-led energy transition. In other words, let's use less before we start to build out the electrical power supply. We'll jump through a bit quickly with time. So I guess everyone has their pet topics and they can relate it to everything. But as we look at a lot of the global trends around, we pretty much see a role for geoheat, ground source heat pumps in most of these things. Industrial heat decarbonisation, green buildings, embodied carbon. We've actually done some work at the University of Wollongong looking at embodied carbon and ground source systems. Electrification, they all relate basically to what we're seeing. So really, the heat pump itself, in a way, becomes right in the middle of a lot of these sort of global trends that we see. And when we look at the evolution of them, and this will make partly sense, particularly when I look at the precinct question that's just been raised. We've had a really parallel path, different timing, but parallel path to the electrical sector. We've both got a goal to reduce emissions. We just have the extra complication of the refrigerants. We both have lower demand now with more efficient appliances, with green buildings, less heating and cooling per square metre as a rule. We both look for storage and digitalisation as part of our evolution. And we're both looking more and more for local and renewable sources. The one area where we actually separate out is on the decentralisation and the centralisation. So, rooftop solar is a perfect example of decentralising the energy grid. But yet, because with the thermal side, we have both heating and cooling, so I guess you want to call it positive and a negative, often the more we centralise or start to look at multi-building systems, the greater the benefits we can provide in the system, particularly when you throw things like thermal storage into the equation. So the electrical world is doing all this. As we know, they've gone from all these emissions as such, and they're making their transition. Some that, it's obviously very much in politically front and centre, as it has been in Australia for a long time. And of course, a true geothermal or a geothermal power plant at the bottom. But in the thermal world, up until recently, we've really still burnt gas and put things and hung things off the side or on top of the building. So what are the other things that we can do when we think about our source of thermal energy? So we look at all these different things and we start to categorise. How can we categorise our sources of thermal energy? Obviously, ambient air is one with air source heat pumps. And without going through the entire list, but we start to look at them as either renewable or non-renewable. Obviously, renewable is our preferred. If it's natural or anthropogenic, to be honest, doesn't really matter. We just want to make sure we're using it sustainably. And then we have all those sources and we throw them into a building, and this is from some of our friends have been kind enough to let us borrow their image out of the US. But then we start to look at all sorts of different things. It's heat from subways, it's using water bodies, it's using building piles, it's getting process heat off energy. It's like all these different things that come into the mix when we actually put a focus on thermal energy, not just thinking about thermal energy from, I just throw a boiler or a split aircon on at the end of the job. So now I'll carry it down into the geothermal side. Our friends at GNS Science have been nice enough to let me borrow this. Whenever you see one of these sort of categorizations, always realize that every site and every application is different, and none of the numbers or the depths or anything here are a hard and fast rule. But as a general rule, obviously, I'll go to the right first and we'll get rid of that. When we get really high temperatures, we can obviously start to look at geothermal power, and that's what a lot of people are familiar with, and what a lot of people think geothermal is, with no sort of real understanding of the heating side of things. As those temperatures come down, then we can start to look at direct heat, and that could be, we've even had projects down to 35 degrees heating swimming pools directly. So you can come really quite low in the direct heat, but a lot of the time the direct heat is going to be sort of 40, 50 and above. But then just because you've got those temperatures, as Simon and as the team just showed, you put a high temperature heat pump on that system, and suddenly you could be producing steam at 120 or 150. And we've had some really interesting projects in New Zealand where we've been doing that. So once we go, and as we become colder as such, then we start to get to what we call more like the indirect or the GeoExchange component. So if the temperatures aren't suitable for a direct use, then we need to look at indirect. And basically by indirect, I try to keep that really simple and say that's with a heat pump, that's with a ground source heat pump. And then what that allows you to do is to do both heating and cooling with that system. And those temperatures will be typically around ambient air temperature for your given location. So, and I know, for example, in New Zealand, they have a legally 30 degrees and above is geothermal, below 30 degrees is not. Whereas we'd more say that if you're around ambient air temperature and there's no geothermal influence, then that's not geothermal. As soon as you start to get above your sort of ambient air temperature, approximately temperatures, then you're starting to become geothermal influenced. It's very much a site-specific categorization. So when we've got direct, and just quickly on the images there, cascading off a power plant on the bottom left for greenhouses, for horticulture, obviously your hot springs, which everyone's really familiar with, but then direct cold water as well in Toronto, where they're pulling water out of the bottom of the lake for direct cooling. So when you've got the direct temperatures, typically you don't need a heat pump, you're using it directly. But typically you can only do heating or cooling. Normally you can't do both, for kind of the obvious reasons. And the sources are things like geothermally heated waters, hot springs, power plants, wastewater of industrial facilities, etc., and the lake. When we go to the indirect, which is a lot, and now indirect means that we can do it pretty much anywhere in the country. We're not reliant on a geothermal resource. We do need a heat pump because we need to start to actually be able to take that 18 to 20 degrees, which is typical in Australia for ground temperatures in the top 100 metres or so. And we want to be able to, produce whatever we need in the application, 40 degree for underfloor heating or to heat a pool or whatever it might be. But the good thing here is now we can do both heating and cooling, and the ground can become a storage, basically a great big thermal battery for us. So it starts to give us actually a lot more flexibility in our applications. And of course, these ground temperatures, humans have been using them for for much longer. So just a really quick graph just on ground as thermal storage, because one of the things that we see is really so often missed in design of systems. Just got a typical graph here of a building, an office building, sun's down in Tumut. Blue line is the air conditioning needs through the year, obviously it disappears in winter, and then red line being heating, of course. So effectively what we're doing here, we got a heater rejection. So in air conditioning mode, we're getting rid of heat out of the building, we're ejecting it to the ground, and then we keep it there. And we'll keep it there for a couple of months and then we'll pull it back out again in winter. So that's what we'll call like sort of annual or seasonal storage. And then again, of course, at the end of the year, then we start to put heat back in the ground again. But we can also do that very short term. So we can do that over like kind of minutes or hours. So it might be heating in the morning, cooling in the afternoon, heating again at night. So we basically just got this interconnector, if you like, between the building and the ground. And we're just pumping water up and down with that temperature differential to provide us the heat when we need it. And that's where we see things like I'm not sure if that buzzword or trend was up before, but circular economy stuff. There's even an argument obviously for a circular economy element of this work because we're just recycling it. Applications, is there a sweet spot? I wish there was. I wish it was really easy to say that. After you've got all these things and all these different building types and everything, it all depends on obviously how much you need heating and cooling your facility, what your climate is like, what your ground conditions and your ground loop costs, your ground heat exchanger costs are like, how often you run the system, is there a revenue generating option, which there might be on a district style system. So is it just practical to install to drill a hole, or is there no room to do that? There are so many different types of elements that come into understanding even the basic business case for a system. So it's one of those things that people go, oh, we can't do it for this reason. It's like, yeah, but this other reason is actually stronger, and normally it's not, but in this example, it happens to be. So it's very, very site specific, which I think is also one of the barriers for the technology, because a lot of people look, oh, basically it's like, I can't just make a really simple decision on yes or no here, so therefore I'm not going to do it. And in terms of that, like lots of sweet spots. So, you see projects around like in the Canberra is a really common. Canberra actually has a really good climate for the system. So bottom right's like Geoscience Australia. Most people know about that, know about the building. It's been there nearly 30 years now. The opposite corner is a war memorial, which has been, which is going in at the moment. Projects in the snow, projects in the desert. The pool on the top right actually is kind of one of our favourites because we've got 35-degree water heating the pool. And then after we've done that and pulled the heat out of the pool, we then run that water through the heat pumps to heat and cool the facility, including the gymnasium, other things. So it's a combination of direct and indirect thermal energy in that project. Sydney Harbour, Brook Street Pier down at Hobart, all these places are using either closed or open loops in the harbours or in their water bodies to provide heat and cooling. And going a bit further abroad, University of Wollongong, I've got to put it up there, obviously, that's my contract. Sustainable Buildings Research Centre on the top left. So that was one of the first living labs in Australia. They've got a really nice play system there, if you like, with more valves and whatever you can imagine. But even projects like Bird's Nest Stadium, Beijing Olympics has got about 100 holes under it. Microsoft in the top right, Google in the bottom right, who are using actually the building piles. Microsoft have just announced another project, Buckingham Palace of Versailles, putting a system in at the moment. And a nod to probably the original in Australia, which is the Opera House, using the harbour. So that's moved away from geothermal slightly when I talk about these water bodies, but effectively it's all the same concept. It's all part of that bigger concept of renewable thermal energy. I whizzed through that, I think, but hopefully that was useful. And I'll let the next person go.
Brilliant. Thanks for that. Yeah, plenty of good takeaways there. The New Zealand project producing steam. Gee, I'll see if we've got time. I'd love to go have a revisit of that one, get some more on that one. Sounds great. But I'm hearing you there, quite site specific.
Very, very different geology as well.
Oh, over in New Zealand, indeed.
Yeah,
They've got much higher temperatures, yeah. But yeah, I'm hearing you with saying very site specific is when it's going to be applied and appropriate. So it's not so simple, straightforward to say yes, no.
That's right, and a lot of people are looking for that, unfortunately, because boilers over the years or everything, you just put it in. So that extra complexity up front can be off-putting.
Good. And there is going to be this choice and this trade-off here, and it's going to be often the way things are going forward. It's going to be as an air-sourced heat pump or ground source / 4-pipe heat pump where you're using waste heat or geothermal. This is the sort of decisions coming forward. And I thought we'd bring in Stiebel Eltron to talk about this and talk a bit about the two different methods. And one thing on Stiebel Eltron I'll say is, and you can see it in the background there for Tom Stephenson's photo. People often ask me, say, what heat pump should I choose? And one of the mechanisms I say, or one of the reasons you think, okay, who's been doing this a long time? If they've been doing this a long time, that's usually a pretty good filter to work out which way to go. And Stiebel, 100 years there, Tom. So congratulations to Stiebel on that one. But welcome here today to talk about this air source versus ground source. So you've been doing this for some 20 years and doing Stiebel does both sides, air source and ground source. So coming from being able to talk about the positives and negatives that you see from each side or the attributes for each one. Tom, if I can hand over to you and get you to share your screen and take us through this these technologies and these options, and I'll say the hidden benefits, say, of geothermal heat pumps.
Yeah, thanks, Jared. And thanks to A2EP for having me to want to present. Quite interesting listening to the other panelists. So as per my employment contract, I'll rip through some obligatory marketing slides to, I guess, explain a little bit about who we are. For those unacquainted with Stiebel Eltron, as Jared's mentioned, we are that little German family-owned business that's now been in operation for just 100 years this year, but more importantly, 50 years of heat pump experience. So we are still family owned. We operate in 27 countries globally, and we've been in Australia now for almost 30 years. Important to mention that we are, I think, Germany's largest heat pump manufacturer, and around 5-6 years ago, we acquired now Scandinavia's largest heat pump manufacturer in Thermia, which is produces only geothermal heat pumps. So the head office would actually want me to be saying that as a manufacturer of air source and ground source, we love our children equally. So understanding this is not a an air source bashing exercise, but essentially when we go into a comparison of air source versus ground source, we need to explain the differences for consumers to make an informed decision on which pathway they take. So when projects are brought to us, we'll often look at the value of the project and the needs within the project, and look at the best solution to provide that is going to fit the needs and the requirements of the client. Important to probably understand that the first question that we get asked when we propose ground source heat pumps is, what's my ROI? What's the payback? We'll always tell the client straight up, the use of the geothermal heat pump alone is often not justified just on the energy savings. So we need to start to look at all of the other fringe benefits or additional componentry that comes into play with air source solutions being applied to buildings. So we're not looking at a plant-to-plant cost, but a project-to-project cost. Also, we see that, particularly in various comparisons, that air source values and probably even ground source performance values are generally underrepresented or underrated. We have a very strong resource in our ground temperatures in Australia, and certainly access to water bodies, as Yale's mentioned, which sees us achieve much higher values in actual performance than stated on brochures or as represented by EN test values. So normally we'd be guiding our clients on an air source heat pump performance range of somewhere between a COP of 4 to 5, with a ground source comparison of 5 to 7. So realistically, the ground source is probably performing much better than that in certain applications. But as Yale pointed out, every site is conditional. So the big thing I suppose we need to mention when we talk about the comparison between air source and ground source is that we don't generally need to factor in derating of the systems. So if we've got a 100 kilowatt load, we're designing a heat pump solution for 100 kilowatts and not necessarily providing 150 kilowatts worth of heat pumps because of circumstances throughout the year and peak climate conditions that would see those not be able to reach the peak demands. So oversizing is less prevalent with ground source heat pumps, which is important from a costing perspective because it decreases then the ground heat exchanger or the water body exchanger, whatever it may be, to equalise that cost benefit argument. Some other considerations when doing comparisons, bearing in mind if we're talking in a general heating and cooling sense, our heat emitters in the building will always be the same. We are talking about water-to-water heat pumps in the comparison versus air-to-water heat pumps. So leaving the DX side alone for this presentation, if we've got a water distribution in the building, the infrastructure is going to be the same, whichever the solution is. Generally, as a typical statement, we'd say that air source and ground source will be very similar in cost for the same capacity. The only exception in terms of comparison in cost is going to be the installation. You've got plumbing on both sides. And then furthermore to that is then the cost of where are you getting that source from. So if it's a conventional closed loop ground heat exchanger, if it's a water-based heat exchanger, be it open or closed loop, and that's the variable figure. So all of these next few slides will go into explaining how then we justify the cost above and beyond the energy savings of that 30, 40, 50% better performance. So we want to talk about then the hidden benefits of geothermal heat pumps. These are things that we need to discuss but aren't necessarily prevalent on a brochure, for example. Looking at the space saving, first and foremost, and obviously the bigger the systems, the greater the space savings typically become. Air source requires space, not just in the layout, the equipment, the evaporator and the unit or condenser, be it a chiller. But we can consolidate the ground source equipment into a nice, neat plant room, which is preferable, which then plays into further benefits in future slides. Really, for us, it's a question of what you can give back to the client. Can you give them back a car park? What's a rooftop? Extra square meters that they can utilise for solar PV? Is there open ground on site that we can utilise or can hand back to them? And then really, what is the dollars per square metre rate for that? We had a recent project that got switched from an air source solution to a ground source solution on the North Shore of Sydney. And the comparisons there to the builder were a square meter was, or a car space rather was around about $450,000 value to the client. And I guess achieving further environmental tick boxes. Can that previously designated plant space be reallocated as green space? The connected load savings is a big one. So for electrical connections, we know that heat pumps use electricity, ground source heat pumps will use less. But in consolidating all of those services, because we can heat, we can cool, we can do potable hot water, we can do pool heating, any of your thermal activities. So bringing all of those connected loads of individual devices onto one greater system provides some benefits there, not just in the calculation of the connected load, but then also the cost incurred by having that excess electrical infrastructure. Then from that, the system then can be cascaded to build higher capacity or build the redundancy into that system. Certainly an approach for us is to have some thermal storage. And as Yale mentioned, geothermal should always be looked at where we can have a combination with renewable energy, and having thermal storage above the ground as well as below the ground is also a huge benefit to flattening those peaks. The big one of my favourite pictures from a famous Facebook group. Really, it's eliminating plant off the roof or from the side of a building or a dwelling, something that's attached to the facade of the building. I'm sure architects don't sit there in the lunchroom and decide to do this sort of stuff, and they don't create renders where they're plugging air cons in down the side of a building. The building services coordination obviously too becomes a much simpler process when the HVAC is considered during the planning stage. So not just from a basis of geothermal, but just in general. But the geothermal provides a solution where those solutions, of course, need to be designed in early, and the conversations need to occur early. But the consolidation, you're not ending up then with exterior plant bolted to the side of the wall and visible condensate lines. Of course, too, the space saving can be acknowledged for its visual benefits from the previous slide. Acoustics is a big one, probably not so much in the commercial sector, but certainly in some of the residential projects in Melbourne and in Sydney, in probably more affluent suburbs where there are 0 decibel limitations nominated by local government bodies, because in those suburbs, having no floor space ratio, being able to build boundary to boundary, your neighbour is generally somebody. So having feuds over noise from HVAC equipment is very easily mitigated through the use of, firstly, internal plant, but internal plant that makes little to no noise. Having no fans or being air drawn through the machines obviously result in much lower sound outputs as well. Longevity is a big thing too, particularly where I am based in Sydney. But in all reality, it's an Australia-wide problem, given 85% of Australians live within 100 kilometres of the ocean. So we've maybe not seen extremes like the picture attached, but we essentially experience those effects, be it your vehicles, be it your house, or you go down the beach, you see the effects of living in the coastal environment that we've become used to. From that, obviously, air source units will inevitably have a lesser operational life due to external placement and obviously the need to draw air through the unit, and particularly as we get right on the coast where the consumers that generally have higher heat loads and cooling loads because of the nature of their builds will need to have a greater volume of HVAC equipment. So it's a higher capital cost for those guys as well. So we would be essentially budgeting out consumers on the basic, on a typical life expectancy of an air source heat pump, somewhere between 10 to 12 years, sometimes less if you're in a critical coastal climate like the right-hand picture. A ground source heat pump, if well maintained, will and can last greater than 20 years. And I think, as Yale touched on before, I mean, there's projects in Australia that have been around for 30 years or more. And the machines are probably coming up for end of life replacement, but are they really end of life, or are they just getting that upgrade from older technology to something newer? So from us, I guess a bit of a snapshot of where geothermal is being utilised. Richard, who will follow, will obviously talk about some installations from a residential perspective, but the focus, I suppose, in recent times of some commercial buildings utilising heating and cooling and closed-loop geothermal. Canberra Grammar School, which has, I think, swept the floor in a number of different aspects of award ceremonies recently for the building, for the HVAC equipment. This is a auditorium at a private school in Canberra that's fired by around about 0.5 megawatt of ground source heat pumps, doing both heating and cooling simultaneously. No potable hot water on this one. The Reside on Money project in Northbridge in WA was a bit of a proof of concept project, and this is doing hot water. So utilising high temperature heat pump by way of, when we talk about high temperature, it's not in the steam range as previously mentioned, but up to 75-degree flow to give us potable hot water generation for a commercial application in a 22 apartment class 2 residential building. This has been running for a couple of years. We've been mapping the performance, and the beauty about this being open loop is that it's straight into the aquifer below, shallow aquifer below Perth's urban area. COP, including the reticulation loss, sits at about 3.3. So very good stable performance out of that machine, including the reticulation losses. The big kicker to this one is that the embedded network provider who's funded and operating this plant also has solar on the roof that they own and operate, and it contributes a high percentage of on-site renewable energy generation into this plant on a daily cycle. A little bit closer to home for some of you, Kristian, the Melbourne University Trinity College student accommodation. It was completed in 2019. Something happened shortly around that time and the world closed down. But up and running, I think, since mid to late 2021. There's about 104 room student accommodation, heating and cooling, fan cores for cooling, radiators in each room for heating. So first job with the Thermia branded, first and only, but now sold in Australia as the Stiebel branded machine. But again, a great opportunity to conceal a fairly large plant, which on a building of that sort of stature and appearance in an old fraternity like Melbourne University was a good way to hide that sort of capacity of HVAC equipment. That's me.
Tom, many thanks for that. That gives us a bit clearer picture of when and where. And Trinity Grammar, we're hoping to do a tour of that in June or July, so we'll watch that one very closely. Thank you. A little takeaway there for me, because often we've said about space being a constraint in a building to change to get off gas. And so it's usually a matter of imagination and just cost. But car space at $450,000 of the value there, which is probably the sort of space that you're going to need when you go to get off gas and put in say, an air source or so heat pumps. Like, wow, that's some cost there. So I can see this is why that brings the ground source back into play. Brilliant. Thank you. And so on our final stretch here for our presenters, let's get into the deep practical side. And then we're going to start talking about policy. Hopefully our team has seen the question come through, the early question come through about policy, and we're going to have a chat about that. But before we do, I want to introduce Richard Jefford. He's the Managing Director of Highlands GeoExchange, and they're a specialist at heating and cooling and have been doing these installations. And I know Richard's very close to seeing and watching oversight of these installations, and can give us some real insight about when and where for geothermal heat pumps and some good tips there as well. So Richard, over to you.
Thank you. The world's best kept secret. So it was a cold Tuesday in July 2011 when I arrived at a house to see my first geothermal installation. While I was waiting for the engineer to arrive, it started snowing. So I live in a very cold area. It was a familiar home. 3 years previously, I'd been repairing gas boilers on this site. So to a tactile person, plumber, I needed to see, feel, and touch for myself. How does this work? When you see with your own eyes the positive temperatures coming from the ground on such a cold day, it's compelling. In my region, 70% of the annual load is winter heating over a 12-week period. So moving forward in time, 12 years and hundreds of heat pump installations, I still get the hairs standing up on the back of my neck when we turn a machine on, seeing the positive outcomes we get from geothermal. Geothermal is a gift to us all. A little bit about me, some of the products and partners we deal with. We want to be capturing, as been mentioned by all of the experts, capital cost and how do we apply the most practical in every application. Everyone just about has spoken about taking a holistic view. Where can we capture our energy from? Where can we leverage our energy to get the best for the applied need? And as Yale said, and others, what is fit for purpose for that application? So for me, back in 2018, we were dealing with different manufacturers of heat pumps. I felt there was a need for equipment that did more. I was looking for variable speed water-to-water machines, and we ended up finding EcoForest as a brand. This machine that's pictured here, and similar to Euthermia products as well, it's an all-in-one product. We've got domestic hot water built in. It's actually currently the only unit with watermark is in an all-in-one residential type machine. So again, it's how do we capture all of the equipment in the smallest footprint space. Real estate, is these days, since COVID, ridiculous in every form. So how do we capture, how do we get the best bang for our buck for everyone, builder, architect, client, and having the equipment doing the right job and all of the services we need. Case study, in Barrel, 30-year-old house. So this home was on a gas boiler, retrofitted. It had radiators and domestic hot water off a gas boiler. And we were looking at the challenges of a very steep block, elevated home, weatherboard, no access for drill rigs. The equipment that we use is able to use 3 different sources of energy. So the machine can decide where is it getting its energy from. We're working with a project at the moment of a dormitory, and we're looking at capturing the waste energy from the sewer. The average temperature from the sewer is 21 degrees. So at high ablutionary times, we've got a massive resource that we can use before it goes to waste. Now, that's one source. So these machines with this inbuilt technology, we're able to look at temperature during the day and micromanage not just from an annual perspective, but down to an hourly or an instant perspective. Is air better? Is ground better? Is a combination of both. These machines I'm talking about here are all water to water. So they are then leveraging the water aspect, whether it be in this picture, you can see they're actually 2 dry coolers that we're able to do our water exchange with air, not refrigerant, but water with this. Couple more pictures there. So had radiators in it. What we were able to do is actually add some fan coils into this system, which gave the separate system and a split system to be able to give cooling as well as hot water and heating. So forced air, the capacity of the radiators are undersized generally from a gas boiler when they're initially installed. You've got this very high temperature, 75+ degree design. The technology in heat pumps are getting better. There's natural refrigerant heat pumps that are able to deliver 70, 75 degree constantly. So the retrofit market is becoming easier and more available with the newer technology. But this existing home, we were able to leave the existing radiator solution, add some fan coils to boost the heating in winter, but then have the separate ability to do cooling. all off the one box, whether it be heating in the morning and cooling in the afternoon. While this machine is running, it's also delivering or able to capture waste heat through its HTR system and deliver free hot water or pool heating while it's running. This particular machine is able to do it whether it's in heating or cooling as well. It's a Spanish machine. Next slides here, we've got home in Robertson, large new build, some big air changes per hour, not ideal, but obviously the built environment has a massive impact about, we can design everything in theory, how well we're going to deliver this project and what our efficiency are going to be, but what is practically delivered. So having everyone on board, it's a multi-sell in the residential space to so many stakeholders, you know, from the builder, the architect, the owner, all the other trades as well, have to have a share of understanding to deliver the best project possible. This home's got horizontal loops, so it's a rural application. Obviously, again, every installation's unique. Where is the best place to get our energy? What's the most cost effective? And so this home, we've got plenty of space. Horizontal ground loop was what was selected in the end. And we've got a plant room there with 2 heat pumps cascaded. Rural location, so power supply was an issue. To upgrade the power to this property for conventional equipment would have paid for the geothermal twice over. So when you start monetizing to the stakeholders of exactly where your return is, well, what are we going to value the return and where are we measuring our return on investment? It doesn't have to be an instant payback. You can also take the capital aspect of alternates into play. A couple more slides of the installation. So 2 separate hot water systems splitting the home, large floor area for floor heating and hydronic floor heating, and then 3 large ducted fan core units to do heating and cooling, and then we had provision for pool heating. The 2 heat pumps, each heat pump was connected to its own hot water system, which is why we've got a slight variable on the SPF, or which is the seasonal performance factor. When we're measuring, COP is for heating only, you've got EER for measuring cooling, obviously. So these machines are actually combining EER and COP to give you a seasonal performance factor. So energy in and applied energy out. Another one, third one is in Glen Quarry. So new home, again, large footprint, very well insulated, good solar orientation, good design loads when we started, and it's been a great one to deal with. So from an installer perspective, this is where knowledge in the industry for installers is vital, and probably another missing link for government to be looking at is education. Moving forward, we need more people knowing about it. This has got a burnished, so a polished concrete floor. Now, in the Highlands, when we're getting down to your -5s, you know, walking on a concrete floor can be a very scary proposition in winter if you don't have some sort of heating on the slab. And conductive heat is obviously the best for humans. Walking on a warm floor, there is nothing better for humans. It was a it was a very tough decision for the client to really get them to engage in the fact that they've got this beautiful solar passive north-facing glass, really tall, really broad glazing, which is on the other side of this image on the home. And you know, you've only got to have half an hour of direct sun, and that place being airtight is warm in moments. So if you've got a thermal mass of your battery, a second battery storage. In other words, you can overheat very quickly. So you're going to need to reach ultimate comforts for clients. You are going to need to have forced air for cooling, something that reacts quickly. So they were on a tight budget, working with these clients, getting them to accept that was going to be the case was challenging. We got there. They didn't do floor heating in there, and they said I've got testimonials where it is the most comfortable home they've ever lived in, and they've kept moving and lived in quite a few, which was just absolutely so.
Richard, I think we're just about out of time there. If we can just wrap that one up.
Sure. So just going through the rest of the installation, some testimonials. So look, I can finish it off at that. Thank you all very much for your time, and thank you everyone to the guest speakers as well.
Yeah, thanks for that, Richard, and lots of lived practical experience there. So many thanks for that that summary there. Kristian, if before we get to the questions, I might just throw to you and any sort of reflections and comments coming back from those fabulous presentations there.
Yeah, I think lots of good stuff coming in, Jared. I especially appreciated the fact that there are all these other, if we want to call it ancillary or hidden benefit to ground source heat pumps beyond the improvement in the COP. And I think it's useful, as many of our guests have mentioned, how logical it seems when compared to an air source heat pump, where we're just pumping the heat from outside the building inside in winter, and then in summer we're just doing it the other way around. We're pumping the heat from inside the building to outside. It just seems much more sensical to me from a first principles approach to have that heat stored somewhere in the ground where we can reuse it and sort of like close that loop, if you will. So lots of food for thoughts.
Absolutely.
Today.
It has to make sense, has to. And if I can bring in the whole panel here, and the big question's been raised. It was raised early on in the Q&A. What kind of policy incentives do we think are needed to economically incentivize developers for future geothermal heat projects in Australia? And clearly, if it makes money, the more likely it is to be implemented. And are those policies on the horizon? And so if I just kick something off to say, I know that obviously we've got air source heat pumps being part of the deemed methods within the VEU and the and for ESCIs in New South Wales, but yet ground source not there. And I understand it's from their perspective, from government perspective, they're like, well, the predictability of an air source is a bit better when you look at different climate zones, and the predictable performance of geothermal maybe not as clearly laid out and as obvious when it comes to air source. Yale, maybe we'll start with you. Comments on the sort of policy incentives that are needed to incentivize geothermal heat projects and ground source.
Look, I think it's an interesting point that what you just made there about the predictability of COPs, etc. Whereas it's probably a reasonable argument that a ground source has a much more consistent COP all year round, so therefore is actually more predictable and more variability. I'll leave that one alone. I'll put that out there and leave it. One of the things that we've seen, and that does exist in parts of Europe, and it's because obviously the cost and the potential risk of drilling is such a is often what puts people off, particularly more so probably with the deeper, like direct stuff than necessarily the closed loop, the shallower closed loop, indirect stuff. But there's various insurance schemes around, so that you can, if you go and drill a hole, you spend $1 million or whatever on your hole and you don't find anything, then you're covered by an insurance scheme. And some of those are state-based. So that is the sort of thing that, at least, it's still, I guess, arguably a market mechanism, even though the state's involved, but it is helping people sort of a little bit overcome that initial cost of some exploratory drilling work.
Gotcha.
I'm sure the guys at the LBA could talk through that one as well.
We'll keep going. Well, I'm going to take you back onto that COP, though. You said it arguably, or you say it is more predictable, the COP for geothermal. And I'd say yes, but what's that? That does rely on how that the pipe works through the ground and what have you. How that's done, doesn't it? Isn't there a relationship between that? So I've got a piece of equipment. Depending how that's piped up into the ground, have I gone deep enough with my wells? Have I done enough underground pipes like which Richard showed? Isn't there some variability on the installation there?
Yeah, yeah, I understand what you're saying. I think there's also a lot of variability in how people position and place air source heat pumps, which I think is probably ahead of an inquiry in the last few days on some of those schemes. And I can see the heat pump suppliers just nodding and laughing about that. Because there's been some terrible, obviously, examples of, particularly in the hot water space, I guess it is, they're just putting them in cupboards basically and saying it's going to work. So I argue that for both systems, there's a design/installation risk that applies with both. So the caveat would be, I guess, that a system properly installed. And so it depends on then how you want to police that or make sure the systems are installed properly. But once you've got that system going, we know the ground temperature is not changing. So, and if you show the design, you can prove on the design what the entry water temperature into the heat pump is going to be consistently through the year, even over, like, we can model them over like 20 and 30 year periods. So then we can actually know what that system is going to do and have much more certainty over its performance.
Gotcha. And Tom, anything to add to that, either on that consistency of the COP or just policy in general? Your thoughts on that?
Yeah, I guess we don't need to go into the topic of what's happening in the hot water heat pump space. I think that's pretty well known. That is essentially a risk, and we probably see that in the domestic air to water heat pump space. It's becoming commoditized as governments push towards electrification without proper frameworks and standards to support the invested businesses, whether it's manufacturers or installers. We are seeing cowboys come into that space. So really, I'd say the risks are no higher or lower on ground source because you always have an engineer involved on the ground source. You always have qualified technical people, installers, mechanical plumbers doing those ground loop installations. So I would argue it's a neutral risk, but with much more to gain on the ground source side.
Yeah, gotcha. Thank you. And maybe go to Ash now. You guys are trying to develop a big precinct there, and you're going to have a lot of different users coming and going, what have you. How are you finding the regulatory environment and policy there supporting what you guys are doing?
Yes. So I can only speak from a Victorian point of view. So some of the challenges that we've come up against is firstly the recognition of heat as a resource. So, is heat a renewable energy as such? And can it be classified the same as we might do as wind and solar and batteries? And there's also lots of learnings around, well, if it is a resource, then how do you transfer that resource between people who's the owner or investor and who's the manager of some of this stuff? And then thinking about, we have a geothermal policy in Victoria, but it starts 1 kilometre deep. So really what I guess we're in early conversations at the moment around looking at, well, what about that first 1,000 metres? Do we need to create a shallow geothermal policy? That's a big, long road for, creating policy and regulation, or is there something that we can amend? Because essentially our resource in Victoria lives within the water policy, and the regulations and I guess tools to manage that don't quite fit, because to get access to water, you need a water allocation license, and if we have a closed loop system where you're putting back as much as you're taking, then you need a zero allocation license, and computer says no, because that doesn't make any sense. So there's lots of regulation and lots of work going on with the compliance and regulatory people at the moment. So did you want to jump in, Yale?
Yeah, I thought a couple of years ago, geez, sorry, 8 to 10 years ago, the Victorian government changed their water extraction, I'm just say regulation. I forget which one it was. I'm sure I've got a copy somewhere.
Yeah.
Such that if there was already a cap on a groundwater catchment area, and you're near that cap, if you did a pump and dump style system, like or closed loop as you're calling it, so you're not extracting any water, but it goes back, then it doesn't add to the extraction level for that groundwater management unit or that groundwater catchment. So therefore, it didn't stop you from getting a license, like a water take license. But maybe it's not fully implemented or something, because it was all before COVID. So who knows if everything just came to a screaming halt during COVID.
Yeah, and I'm probably not quite the right person to answer that, but there is work being done with Southern Rural Water and some of the other water authorities that manage groundwater, and what does that look like? Because it's a case by case. I guess what you just touched on then is very applicable in Latrobe Valley, where we've got a 100% allocation of the aquifer, and then how do people get access to that without going through pages and reams and reams and reams of applications and licenses? So
yeah, exactly. And the intent of it originally was to help, as I understand, to help encourage like the geothermal hot springs industry.
yes.
And then when we actually did the review of it, we suggested that they changed the language because it's just about taking heat. So we got them to change the language to take heat and cool, sort of, so it could be both a heating and cooling system. But yeah, that was my understanding. I said maybe it didn't get fully implemented if you're hitting that as a barrier.
Yeah, and there's other things to consider around if you're extracting water from an aquifer and then want to re-inject that water, then that goes over to the EPA, and you need a license to re-inject water back into the aquifer as well. So.
And so no doubt similar when you're into the harbour or the rivers as well. So,
yeah.
And actually, wasn't there a problem associated with when you take the heat out of the water, the EPA treated it differently when we're re-injecting that cooler water back down? Was it the same, et cetera, et cetera?
Yeah, so it gets classed as a wastewater. So whilst there's nothing wrong with that as a regulation, for the engineers in the room, it's still the same water. It hasn't come into contact with the atmosphere. So, there's lots of people shaking their head, but, that's the current regulation we've got at the moment. And, if we want to activate and grow this sector, I think probably lots of it might need a review or just to look at about how do we advance the geoeconomy, as I call it.
Absolutely. Good. And no doubt needing some research there to back up any sort of changes, no doubt.
Absolutely.
We bring in the universities. And we've got a question on temperature, and I'm going to get to that in a moment. Just want to give Richard, just before we close off the discussion on policy, anything from your side to add to say this, what would help supercharge geothermal heat projects?
Well, when we talk about the heat pumps, it's also classification. I mean, Yale touched about insurances on drilling. The government should be able to accept, with engineers signing off, what guaranteed COPs are going to be performed. That there's a lot more assurance in what geothermal can offer than other technologies. It's backed by a lot more. But we've got education as well as acceptance. So in my space, machines that have got combination hot water built in will not be recognised by federal government. They deem it as a novel technology. So it's very disappointing to see that the federal government is not looking at it. Obviously, the space is changing with the STCs and the renewable credits there. So they are looking at it, and they're trying to get rid of their current expire their current solution first, but they need to be looking at support on these type of solutions, whichever framework we can get that makes sense to them. But when they deem it as a novel technology, it's a retardant for our industry when they do that.
Thanks, Richard. Something to address. Another. We'll add it to the list. Done. There was a question, great question here, is how high could the temperature be with additional heat pumps, suggesting max 150. Yale, you had some thoughts on that one, and I'll probably throw it to Simon as well.
I pressed the button accidentally, but I'll make a quick comment, and probably Simon's best, even better placed. Yeah, that 120 is what we're seeing as the main guaranteed at the moment. But in speaking with manufacturers, both Simon's group, but also elsewhere, I've seen definitely 150, 160 being talked about positively at the moment. And I've heard whispers of sort of 200 and things, but whether or not, or it might have been, the very positive marketing guy saying that in 2 years I'll hit 200. Then maybe Simon can fill in a bit more with that. But it's definitely, those temperatures are definitely realistic now.
Yeah, 120 is a very standard product, as you say. Yeah, 150 is doable, and there are commercial products on the market. Going a lot higher starts to become a bit more of an experiment, I'll say, or a bit more of a breaking new ground kind of thing. But certainly 150 as an output from the machine is certainly doable, but costly. It's quite an expensive way to go. 120 is much more cost effective.
And if I'll throw back to the webinar we had at the beginning of March there with gas. If you go through that, you'll see that 150 plus is certainly becoming more common. And you say if commercials at 120, it's commercialized. You get the feeling that 150 degrees is not going to be far away before that's a commercialized product, and then then pushing into the 200s there.
There's a pretty big incentive across Europe in particular with with their loss of gas supply to develop those heat pumps. So there's a lot of effort going into it.
And gee, we'd like our universities getting on board like they are in Europe to try and testing a few more of these high temperature ones and getting them out into Australia. So hopefully a little bit of pressure there for Uni Melbourne and RMIT that are working on this. Let's go. Couple of questions here I'll just read out, and you've already answered them, and thank you for that question from Brendan about the issues that geothermal heat source present that you don't have air source, e.g. water chemistry. And a quick one, you've said water quality is important on the open loop pump and dump systems. On a closed loop system, that is not an issue. So
and maybe just clarify there too, because Ashley was using the phrase closed loop for when we're talking about what we call an open loop in terms of the pump and dump systems. So there's I just say across the industry in different areas and different people coming in from different disciplines, different countries and everything, there's a lot of little definitional variations, shall we say. So just always a warning, always just be really clear on what people are saying when they're using various terms like that. So when I say open loop there, I mean a system where you pull groundwater out of the ground, pass it through a heat exchanger, put it back.
Got it. Thank you. Good. And there's a quick question there on solar hot water panels be added to any of these heat pumps, and absolutely they can be. You've said there, Yale, and connecting with the thermal storage and buffer tank, and really good option there. So thanks for pop that answer in there, Yale. Many thanks. And we're just about coming to the end of the schedule here today. So let me just close up with a thank you there. I'm just going to bring up my closing slides, if you bear with me for a second. And so to the team here today, thanks for all your contributions. Great to have that advice from all those angles. So many thanks for your presentations today. And to Kristian, thanks for joining me there, and great to have University of Melbourne pioneering some of this research work there. And it's not just Melbourne University. Race for 2030, CRC has an excellent program for decarbonising heat and a strong focus and heat pumps. We've appreciated working with them with all the research that we're doing with them. And I know the Race for 2030 wants to see much more happening in support for ground source and geothermal heat pumps as well. And so the researchers are there and ready and primed to get moving on this stuff. Just to close out now, in terms of further events for A2EP, we've got a quarterly update just for our members coming up on the 16th of April. Otherwise, we're going to sort of take it easy for a month after doing 4 or so webinars and site tours and things through April. But don't worry, we'll ramp it up again later in the year. And so if you want more A2EP, go to LinkedIn and follow us there. We're always giving lots of updates and making sure you've got the latest information on what's happening with heat pumps and renewable heating and energy productivity, of course. So that's it from us today. Many thanks for joining us. Many thanks to our excellent presenters here today. The slides will be coming out next week, and along with the recording. If you missed anything, you want some more data, we'll also send out all the contact details of our presenters here today as well, so that you can get directly in touch with them if you have some further queries. But thanks for joining us today. All the best, and have a pleasant afternoon, and we'll look forward to seeing you at the next webinar. Thank you and goodbye.